Hello everyone. So while reading the book Electromagnetics by Stephen W. Ellingson, I came across the theoretical explanation about why 77 ohm is good for less attenuation and 30 ohm is better for power handling capabilities. So thought of sharing it with you all. Okay, let's see why 50 ohm. Because we always say that 50 ohm is the compromise between power handling capability and attenuation. To theoretically prove that, we have to consider a coaxial cable. So a coaxial cable consists of an inner conductor, outer conductor, and a dielectric in between. This is the cross-sectional view of a coaxial cable. Here we can see an inner conductor which has a radius of A, and this is the outer conductor which has a radius of B, and this is the dielectric. Its permittivity is epsilon r, conductivity is sigma s, and sigma ic is the inner conductor conductivity, sigma oc is the outer conductor conductivity. So in transmission line we can model a coaxial cable has an RLCG circuit which consists of resistor and inductance in series and a capacitor and conductance in parallel. So this resistance and conductance are mainly contributing for the attenuation in the coaxial cable. The resistance per unit length is the sum of the resistance offered by the inner conductor and the outer conductor. So the resistance offered by the inner conductor RIC is equal to 1 by 2 pi A delta IC into sigma IC, where delta IC is the skin depth of the inner conductor and it is very less than the radius of inner conductor. Similarly, the outer conductor resistance is 1 by 2 pi b delta OC into sigma OC, and the skin depth of the outer conductor is very less than the thickness of the outer conductor. So the total resistance can be given as the summation of the resistance of both inner conductor and the outer conductor. So based on these equations, we can summarize as the total resistance is 1 by 2 pi root 2 by omega mu 0 into 1 by a root of sigma IC plus 1 by b into root of sigma OC. So we are going to consider two cases. In first case, we are going to consider that the conductivity of the outer conductor is very greater than the conductivity of the inner conductor. In that case, we can see that this parameter, this factor become very less, and we have to consider only the first factor. So in case 1, the total resistance become 1 by 2 pi sigma IC delta IC into 1 by A. In case 2, we are going to consider as the outer conductor conductivity is same as inner conductor conductivity. So in that case, there is contribution from both inner conductor and outer conductor. So based on these two cases, we can write the resistance offered by the coaxial cable as 1 by 2 pi delta IC sigma IC into 1 by A plus C by B, where this C is equal to 0. In case of case 1, then it will be reduced to only this much factor, and in case of case 2, we will get this expression. So we found out what is the total resistance offered by the coaxial cable. Now we are going to find out what is the attenuation in the coaxial cable and how we can obtain lower attenuation. So this is the equation of the propagation constant in a coaxial cable, which is given by root of r plus j omega l plus g plus j omega c. And the real part of this equation becomes alpha, which is the attenuation constant, and the imaginary part become the phase constant. So what is the importance of this alpha is when a wave is propagating through the coaxial cable, the voltage and current wave will be attenuating by a factor of e raised to minus alpha z, where this alpha, that means the attenuation, is contributed by both the resistance component and the conductance components. So the attenuation constant alpha can be given by alpha r plus alpha g, which is contributed by the resistance and one contributed by the conductance. So the alpha r can be given by r by 2 z0, where z0 is the characteristic impedance of the coaxial cable, and alpha g is given by the conductance, which is equal to g z0 by 2. So by substituting z0, we will get alpha r and alpha g given by these two expressions. So here we can see that the alpha g is depending only on eta, sigma s, and epsilon r, not on any of the coaxial cable parameters like radius of the inner conductor or radius of the outer conductor. But in case of the alpha r, it depends upon the coaxial cable factors like uh, inner and outer radius. Here we can see that our characteristic impedance is depending upon inner and outer radius diameter, and here our aim is to find out when will be the attenuation low, for what value of z0 the attenuation will be low. So to find out at what value of z0 the attenuation will be low, we have to find out the parameters like A and B of the coaxial cable where z0 will be low. So to find out that, we can see that only alpha r has that dependency of B and A. Alpha G does not have any dependency on B and A. So to find out the lowest attenuations, we have to only consider alpha R. So now we are going to consider alpha R, that is the attenuation offered by the resistance, to find out at which characteristic impedance it becomes very low. So to mathematically find out what is the lowest level of attenuation, what we can do is we can take the first derivative of the attenuation and equate that to 0. So what we can do is we are going to take the first derivative of the attenuation and making it to 0. So this is the first derivative of the attenuation, and we can say that for that first derivative to be 0, the factor inside the bracket should be 0. So that will give us ln b by a equal to 1 plus c by b by a. So in our previous case, we have considered two cases, that is c equal to 0, one case, and c equal to 1 case. In case c equal to 0, we are considering the conductivity of the outer conductor is greater than inner conductor, and in c equal to 1 case, we are considering the conductivity of outer conductor is same as the conductivity of inner conductor. So by substituting c equal to 0, we will get ln b by a equal to 1, and which will correspond to b by a equal to 2.72. And in case of case 2, we will get the value of b by a as 3.59. So this indicates that if the ratio of outer radius to inner radius of the coaxial cable is between 2.72 to 3.59, we can expect the attenuation to be lower, considering these two cases. So we have the characteristic impedance, which is related to ln b by a. So in this calculation, we are going to consider the epsilon r is equal to 1, because we are going to consider air as the dielectric. And here we can see that when b by a equal to 2.72, the characteristic impedance is 59.9, and when the characteristic impedance is 3.59, the characteristic impedance is 76.6. So this indicates that when the conductivity of the outer conductor is greater than the conductivity of the inner conductor. When the characteristic impedance of the coaxial cable is 59.9, we can expect lower attenuation. And if the conductivity of the outer conductor is same as that of the inner conductor, we can expect the characteristic impedance as 77, then we can expect lower attenuation. So these are the characteristic impedance that we have to consider based on these two cases. So in most of the cases, we will be using the same inner and outer conductor materials. So our aim is to have the 77 ohm uh, as the characteristic impedance to get the lower attenuation. So the power handling refers to maximum power that can be safely transferred by the transmission line. Because when we are increasing the power inside a coaxial cable, the electric field become very large and it can cause the dielectric breakdown and can destruction on the connected devices. So we have to find out what is the maximum power that can be transferred uh, to through a coaxial cable. So for that we have to consider the electric field inside a coaxial cable. For that we are considering a cylindrical coordinate system with rho as the radial dimension and phi and z as other coordinates. So the electric field is minus delta V, and um, based on this, we will be getting electric field as rho equal to V0 by rho ln B by A. Here also we can see that electric field is depending on the parameter B by A, and we can say that the maximum power is V0 square by 2Z0. We can get V0 from this equation, and substituting this, we will get P maximum as pi E square pk divided by eta 0 by square root of epsilon r into a square ln b by 8. So our aim is to find the B by A parameter for the maximum power transfer. So for the maximum power transfer, what we have to consider is the first derivative of with respect to A should be 0. So we are going to take the first derivative and make it equal to 0. So this is the first derivative, and we can say that the factor within the bracket should be 0, which will give the parameter as b by a as square root of e, and which is equal to 1.65. So when we can see that when the b by a parameter is 1.65, our characteristic impedance is around 30. So this indicates that to have the maximum power handling capacity, the characteristic impedance of the coaxial cable should be 30. So based on the derivations on the book, we got that 77 ohm is the characteristic impedance which is required for the lower attenuation, and 30 ohm is the characteristic impedance required for the better power handling capabilities. So in general, when we consider the arithmetic mean of both these values, we will get it as 53.5 ohm, and if we consider the geometric mean, it will be around 48 ohm. So we can say that 50 ohm is the compromise between the power handling capability and attenuation based on these factors. So we came to the 50 ohm value considering a coaxial cable and air as the dielectric. This is the plot of the characteristic impedance for the coaxial cable RG59, where epsilon r is 2.25, and I have stored the Python script for this plot in this GitHub. If anyone is interested, you can download it from there. Okay, that's all. Thank you for watching this video. The reference to these materials will be added in the descriptions. Thank you.